So I kind of always wanted to have a title like this. It sounds like nice and pretentious, doesn't it? But my talk is about Crux. I haven't gone off and written other bitemporal database during the break. So I've been to Helsinki one time before, 25 years ago, for another computing-related event, apparently Assembly 94. Which, yes! Anyone been here? I was trying to ask, apparently. So I was actually comparing these notes, right? Like it's quite similar. So security personnel, yeah, I guess we have that. We have a central TV system of some form. We have party T-shirts, yes. Ray trace movies, thanks to the earlier talk. Also, there's electricity for everyone. How good is that? Like I hate when you go to conference, there's no electricity for you, right? Everyone else. There is sponsor potentially selling soft and hardware databases, who knows? So anyway, if you don't know about the demo scene, and if, for example, if you're not from Scandinavia or who knows, you may not know, I totally recommend you to check it out. If you're interested in programming, which I think you will be if you're here, you kind of owe it to yourself to know something about demo scene. I think there's a kind of common, it's not a common, but a similar ethos somewhere, like the relationship between demo scene and the Lisp community. But that would be a very interesting talk, which is not the talk I'm actually going to give. But for someone else, I kind of challenge that talk. Someone actually knows more about the demo scene. I was more of a hang-around, right? Like I tried to, I didn't just try to learn, I learned to program assembly, but back then you didn't really have any resources or anything, right? If you didn't know the right people, you could never figure out how they did the stuff they did in the demos. You hang out in the BBS system, whatever. Like there's no Stack Overflow. The internet, of course, were kind of coming around this time. Well, the internet, of course, had been existing for a long time, but the web, etc. Another thing I want to mention about this slide before I start my proper talk, right, is that if you're interested in this kind of stuff, there's a series of books from MIT Press, which is called Platform Studies, and they basically look at things. So the book about Amiga is called The Future Starts Here. And there's another book about Atari VCS, which is the kind of the racing the beam. And they're very interesting. They go through basic case studies, how people implemented fighting the platform, working together with the platform, a little bit like the demo scene. There's probably a very good book about the demo scene. I don't know it. So anyway, if you don't know about the demo scene, that's the kind of like takeaway. Okay, anyway, another thing that also was going on in the 90s, unbeknownst to me, when I was in my teenage years, lugging my Amiga across the Baltic to Finland, was that there was a lot of the research in temporal databases happening. So now my actual talk, right? So a bitemporal table is a glorious structure. So this is a great quote to find in a book, like when you're going to talk about bitemporality. So this is from Developing Time-Oriented Database Applications in SQL by Richard Snodgrass from '99. So, well, this is the end of the 90s, right? So if you go through the 90s, you will see a lot of papers, a lot of interest in temporal databases. And this is basically a book written for practitioners. Like, okay, there are no, all this research, I'm not saying they didn't end up anywhere, they probably ended up some good prototypes, but they didn't really commercialize it properly, or couldn't necessarily for various reasons in the 90s. For example, there was no cloud, disk was more expensive, everything was more expensive, right? The resource reward. So this idea of just keeping all the data, all the history around forever, which a lot of these concepts are actually based around. If you look in some of these old papers, right, they're talking about like the optical layer, which is kind of like when you burn down some data to the DVD or CD. Like that's cool, that's not what we're going to do. So this is kind of the end of the 90s. He kind of summarizes, he doesn't really summarize the research, but he takes some of the ideas from research. It's like, okay, sorry guys, we still have SQL, we still have the normal databases. This is how we implement it in SQL, right? So I'm just going to look at this a little bit. So again, coming back to this, like the bitemporal table, it simultaneously records the history of the enterprise while also capturing the sequence of record of that history, right? So I'm going to try to break down what this means. In reality, my talk is not actually about like what is bitemporality, why do you want it? I want to talk about internals of Crux, but many people have given me the feedback that it's impossible and totally meaningless to talk about internals of Crux unless I give some kind of context, right? So I'm going to try to give you some context, but not too much. Yeah, so what's the bitemporal relation? This is basically a table, right? It's a relation with exactly one system-supported valid time and exactly one system-supported transaction time. So this comes from a consensus glossary of temporal database concept by Jensen, who is one of Snodgrass' prodigies, basically. And it's like a bunch of people in the 90s. They come together, they talk about all these concepts, they don't have a common vocabulary, and they basically create this glossary. In 94, during Assembly 94, potentially. So you have transaction time, may be implemented using transaction commit times and are system generated and supplied. So this is called ingestion time in Kafka, DBTX instant in Atomic, record time is what Martin Fowler calls it, system time in SQL 2011. So one interesting thing is that these guys, Jensen and Snodgrass, they were working on something called T-SQL 2 during the 90s, which were planning to kind of create a SQL standard with temporal extensions. This, well, it came out, right, but it never actually was implemented as far as I know. But eventually, much later in 2011, SQL now has some kind of official support for temporal tables. I'm going to come back to that. So we have valid time, which is the other time axis, right? It's the time when the fact is true in the modeled reality. The valid times are usually supplied by the user, right? So this may be true that transaction time is always monotonically increasing. You cannot go back, like you cannot rewrite the past, but you can rewrite the past in valid time. So you can see this as a kind of, you have a bitemporal plane of times, basically. So this is called event time in Kafka. It's actual time in Fowler. It's business time in the industries. We usually just call this business time. That's kind of like, oh, business time. It's application time in SQL 2011. Again, it's also from the same consensus glossary. So now I'm going back to Snodgrass. So now we're starting seeing like how do you actually model this? Some people may have actually seen this in reality in many products. I've seen it in several products. So basically, you're trying to model. Sometimes you don't model bitemporal. You just maybe model just valid or transaction time, but the concepts are similar, right? Like, so you have to have this kind of append-only thing, like table, where you have beginning of valid time, end of valid time, start of transaction time, stop of transaction time. Often you use some kind of date, like 9,919, like, you know, so someone, like the 10 million bug problem, will have to fix this, right? Basically, all the bitemporal data is not working anymore. So, and also when you do updates, right, you don't actually update anything. You insert new rows. This is kind of a append-only table. You keep updating. So this is like, so if you go back to the actual example, right, so Eva buys this flat in January 10th, 98. But, so this is the current date. Actually, it's not the best slide one, so it's not the best example. But the current date here is supposed to mean that you see that current time is not 98, 01, 10. Okay, but then they realize, like, it actually was purchased the 3rd, right? And they realize this 23rd. So this is one of the things Bitemporality can do for you, that you can go back and change your view of the past without actually losing the auditability of the year. So this basically inserts a new row. It doesn't delete the other row, right? So you get both, best of both worlds. You also get a lot of data. So bitemporal time slice queries takes us in. So this comes again from the consensus glossary. No, actually, it's not. This is from the SQL book. So it takes as input two instances, a valid time and a transaction time instant, and results in a snapshot state of the information regarding the enterprise at that valid time as recorded in the database at that transaction time. So this may or may not be totally obvious what this means, but if you try to break it down, it's basically like these snapshots, they are kind of, if you think about a normal in-place update SQL system, or like set of tables, this is the only thing you have, right? It's always the current state. But this is the thing that allows you to query things and as if it were a normal SQL table at any point of time. So in SQL, here's an example. You basically just use range searches across these things. And this, like, as you can imagine, this becomes relatively hairy. These examples are picked because they actually do fit on the slide. In the book, you will have page after page after page of interesting SQL doing these kind of things. Another thing I can also mention is that maybe you already noticed that once you start inserting and not just overwriting things, your primary keys goes away. A lot of the kind of constraints in normal SQL goes away. So you basically have to turn all of that off, potentially write your own triggers, whatever constraints to ensure that your actual data is correct. Some of it's not totally trivial. Having said that, to Snodgrass' benefit, if you need to do this and you want to do this, you want to read this book. Like, this is a really, really like interesting book, if nothing else, because you may think, oh, maybe I'm going to write a database instead. So SQL query with joins, it doesn't become better, right? Like, you keep adding these things, and you kind of like, you can imagine, after a while, these queries becomes quite hairy. So in a way, you can say that there's no support in classic SQL for hiding the snapshot, right? So here you have to expose it all over the place, which is sometimes what you want to do, actually. But for like the normal use case, it may feel a little bit verbose. Yeah. And actually, as I said, in SQL 2011, you finally have a table, maybe both a system version table and an application time period table. So what this means, this is totally different domain, totally different example, right, from a different paper, Temporal Features in SQL 2011 by Krishna Kulkarni, which is a good paper if you're interested in this kind of stuff, because I have a feeling that time has moved on, no pun intended, from Snodgrass' book to today, right? So there's probably more support. Also, almost every database, like DB2, SQL Server, Oracle, everything has some kind of, like normally in these kind of SQL databases, anything that goes a little bit beyond the standard, they will have something that just kind of is, but it's not necessarily up to the standard itself, right? To be honest, I don't 100% know. I haven't gone off and validated every database and see like how would it actually work. But here we can see we actually for the first time have like an as of timestamp construct in SQL itself. So this is the system time, which is transaction time, right? So you say like, as of this system time, and this period. So you have a way to say, like, so the similar to I said before, the valid time start and valid time end, you can construct a period out of these in SQL 2011 and say like these things are a period and I want to be able to like do application time stuff on that. One benefit of this compared to, for example, Crux and some other bitemporal systems, you can have any number of valid time periods, right? So this is good, right? This also potentially exists and works, so why not? Here is like a closure slide which I consider deleting, but I'm going to try to explain what it means. So now we're jumping out to SQL. So I was thinking this is a closure audience. Potentially this is one way to explain bitemporality to them. I've tried with a few people. It doesn't seem to work, but we're going to try again. So I assume everyone knows the function reductions, right? Because this is the kind of key to understand this slide. So you have a very simple database, which is, so this database only contains one value, despite what it looks right. Like, so think about a single variable keep mutating. And the history of this mutation is the vector, right? But because you use reductions, you will see every previous version of the history. So you're free to basically modify this vector however you feel at any point in time, but you can only modify the latest value. For audit purposes, you will still have the earlier values. So we start from an empty database, we add the value foo, that's version 0, right? So you see in the bottom part, we only have foo version. Then we add a new version, we conch, so my database, I'm conching, bar version 1. So now I have two versions, foo, bar, right? So you see transaction time goes downwards on this slide, and valid time goes to the right. Now we realize, oh, similar to the example with the flat, actually, it wasn't, bar, it was BAS. So I'm changing the first valid time to BAS. So I'm doing a correction at version 0, right? So now we have a new time history of this, and whatever this thing is, this variable. But you see, we haven't lost foo bar. So for audit purposes, we still have the old stuff there. And then, just an example, we do more things in single transaction. By the way, this is not how Crux works internally. It's a little bit more complex than this. But the same principle applies. So I'm not sure if this makes sense or not, but I've thought that this could be an interesting idea. So basically, this is a persistent history of histories. So a very natural way to implement bitemporality is actually using persistent trees, because you can imagine that you have the transaction timeline is a vector, and for every element in that vector, you will have a tree representing your entire valid time thing. And because of the structured sharing between your persistent data structures, that actually becomes quite efficient in main memory. So okay, we're going to talk about Crux. So Crux is a document database. It's also a graph database. And for some reason, this Venn diagram is a bitemporal database with potentially miss. So I'm going to break down the overall architecture of Crux. This is the high-level architecture. So what I'm trying to do here, I'm going to tell you how Crux works on a high level, and then I'm going to deep into how it actually indexes stuff. And if you manage to get through that, I'm quite happy, actually. So Crux basically has two parts. You can transact things, and you can query. This is kind of the public API. It's, of course, more detailed than that, but it's kind of like Crux works in the concept of nodes. Every node is the same. They fire up, and they start building an index. They get their data from Kafka. You can also use JDBC these days, and you can in theory implement Crux kind of unbundled. So there's a protocol, you can implement that with kind of similar semantics. Not as full Kafka, of course, because that would be very insane to try to redo, but like the kind of semantics we need. So when you actually transact something, we take your transactions. I'm going to show very soon how this looks in concrete terms. And we split it up into topics inside Kafka, right? So we have the transaction log, which has a single partition, and basically, because you need the transaction timestamps, right? You cannot have many partitions here. They need to be serialized order. We have the document log, which does not need this, right? We just want to blast a lot of data into Kafka. So this can be partitioned, you can scale, and it's wonderful, except potentially that currently we don't have sharding, so all your nodes need to anyway read all of the documents. This is something we're thinking about and working on. There's 4 operations in Crux, 4 transaction operations. You can put, which is kind of obvious, delete. Again, this is not a hard delete, like it's just a delete saying like you put a tombstone here, right? You have cast, which is compare and swap, and then you have, which is conditional put basically, and then you have evict, which is the hard delete. Because of GDPR and other reasons we need that. And you can see there's a red arrow here which kind of goes against everything else. The Crux node never writes into Kafka itself except for this time. And the reason it needs to do that is because the transaction needs to actually be verified into the node, and then the node says, this is an eviction, it actually passed. I'm going to send the eviction into the document topic, send a tombstone, and I'll talk more about how that actually works later. But suffice to say, this is the only, if you can imagine, you have like 10 Crux nodes, they will all bombard this poor Kafka cluster and say, like, evict this thing, get rid of it. But luckily, that shouldn't be a big problem, because eviction should hopefully not be the main use case. You can see on the left-hand side here, if we're using RocksDB or LMDB, or you can implement yourself. The community implement Exodus, which is a JVM-only thing from JetBrains. I haven't looked at it myself, but it's cool that they've done it. They again comes back to the unbundled thing. We have these protocols for the key-value stores. So if you want to have your own key-value store, you can do. The same people, they actually implemented a totally different transaction log as well, because they were running in kind of OSGI embedded in Atlassian kind of environments. They needed different kind of use cases. They couldn't use Kafka, obviously, but they also couldn't use JDBC. So once we have the things, right, so the documents, they go into document store on the top. All of this is actually in practice usually the same RocksDB instance. It doesn't have to be. So when I say RocksDB now, I kind of just, it could be LMDB, it could be Exodus, but for simplicity, I'm just going to say RocksDB. So it goes into RocksDB. This is a content addressable store, all the documents put there. Same in the document log, by the way, like the key. I'm going to show this soon, so why not? So the bitemporal indexes, they are taking the documents and shredding them apart, taking the transactions, building a timeline, and putting some funky stuff into Rocks as well. Okay, so just a reminder, folks maybe in this audience may not be up to date with the 90s temporal database research, but you may be knowing about time in Kafka in streaming systems. So basically, I already mentioned this, but event time in Kafka is the valid time in bitemporality. Ingestion time is the transaction time. Okay? In Kafka, it also talks about processing time. In the Crux context, that's the indexing time. That's the time when the actual things hit the Crux node, which will be different, of course, at every node. So all of the nodes, they're just dumb replicas of the log, in a sense. They're functions of the log. It's not that smart, right? We're trying to build a system you can actually reason about, which is not too complicated, but you still get horizontal scalability. At the moment, all the data is duplicated everywhere, which is not a good thing, but well, it's going to take us for a little while longer while we're thinking about how to solve this problem. Okay, so they're coming back to the actual real example, right? So this is how you ingest the data. This is the absolute simplest thing you can imagine happening in Crux. You have a transaction, which is a vector, and you have an operation, which is another vector. In this case, you do a put operation, and in Crux, it's a document database. Everything you do is always about documents. The documents are schemaless, so it can be any closure map. They have to be maps, though. We only have one thing, which is this ID, required ID. We're considering how to get rid of this thing, but at the moment, this is the only schema we actually require from you. And there's certain types that can be IDs, keywords, UIDs, URLs, a few other things. You can, in theory, implement the protocol and add new ID types to Crux. There's also an optional valid time. If you don't provide valid time will become transaction time, right? Like that's the default case we write into the database, just the same, you don't know, you don't care. You get some kind of receipt back from Kafka. So basically all this is synchronous, but we get the receipt back. So it's not asynchronous in the sense that there are two APIs. You can get synchronous receipts back from Kafka, or you can basically send asynchronously to Kafka if you don't really 100% care if every message gets through. You just more concerned about throughput. In the normal case, you do the synchronous thing, though. But again, this is synchronous to write to Kafka. It's not synchronous to when the node actually indexes this thing, which is going to happen at some point later when it feels like, right? Hopefully not too long ago, like later. So what you get back is the transaction timestamp, which is what Kafka called a log append time. So this is exactly what we talked about earlier. The transaction time is when Kafka broker decided I wrote this thing into my log, right? The Kafka offset is basically just a monotonically increasing number, which is the offset of the message in the transaction log. Again, we need to have a single partition, right? Okay, so what happens with all this stuff once it hits the Crux node, right? Actually, but first, how do the Kafka topics look? So this at the top here is the same transaction I just showed, right? But I format a slightly different way, exactly the same data without the comments, right? So on the transaction topic, we take this thing and take it apart a little bit. We take the ID, we take the document, and we hash both of them. And then, so this basically, the transaction topic has no actual identifiable data. Of course, you can run some machine learning and potentially find patterns, but except that, like, it doesn't have, in the normal case, identifiable data. So on the doc topic, we put Kafka has this concept of keys and values in the events, and it's partly for partitioning, and it's also for compaction. So we put the key, which in this case is just a content hash of the document itself, and then the document in the document topic, right? So this is how we take it apart. From the user point of view, it looks a little bit nicer, like you don't need to think about this. But behind the scenes, Crux or the Crux API client, Kafka ingest client, will take this and do some stuff. One of the reasons we use hashes, so there are people often ask, like, why don't you use IDs or something? Like, why don't you just, the problem is like you have any number of nodes, right? Like, so it's very hard for you. You don't want the node when ingesting knowing what is foo, right? Like, what is the ID of foo? So that's why we're doing hashes. We're thinking about this as well, but it's how it currently works. There are some drawbacks to this, but let's move on. So this hits the actual RocksDB. And as I showed, there are two parts to this. This is document store. So this is basically very simple. This is a normal k-value store, basically a hash table. We're saying like we have a content hash, we have a document. You can see on the bottom here we have a very low-level API. We don't expect people to use this much as actually end users, but you can if you want to. If you have a content hash, you can get the actual map back, right? Crux uses this internally all the time to actually answer queries, but you wouldn't normally use this level of API. But now, so now the hard part comes. So basically we have two indexes. The attribute value entity index. So in Crux, we index everything you send us on the top level of the document, because we don't want lots of moving knobs. There's no schema, there's nothing, we can just send data in. Obviously, the drawback of that, you get a lot of data, right? But on the other hand, we'll solve that problem at some point, right, by adding more disk. So we see this basically, you can see the key space here. You can see the key is basically, you can imagine it being a flattened tree. So you have 4 parts of the key. The values here is actually empty because we don't care about the value. We just want to have like some way to identify these attributes in the map. So we take the name attribute here. We have hashed the name, which is the attribute ID. We have encoded the value, which is kind of lexicographically, so we can do range search, basically. I'm not going to talk about it. But then we also hash the entity ID itself. And then the content hash here, the final part of the key, is the version, right? Because if you imagine you're writing many versions of foo into Crux, they will give different content hashes most likely, because you probably do some change to your document, right? So at the bottom here, you see if you actually run this Datalog query. So in this case, right, I know the value, which is bas. I know the attribute I'm actually going to look for, which is name. So that means you have the 2 first parts of this key available to you. So we encode that. I'm not going to explain exactly how the query engine works, but in this simple example, we will encode that to the prefix of this key, and then we can scan that prefix and find versions of foo or other attributes for that matter, or other entities for that matter, which happens to have the name bas, right? Okay. The attribute entity value index is the inverse of that. So basically we happen to know the entity ID foo, but we don't know the value, so it's kind of just the other order. As you will see here, the entity ID and the content hash, they hang together because they have to hang together. The early version of Crux didn't do that, that was a mistake. Because the content hash is the version of the entity ID itself. So they are kind of, once you know the entity ID, you get the content, a potential content hash, which may or may not be visible at this point in time, which we will then go into a third index. So this is where the transactions end up. So this is the valid time index. So this index also has 4 parts. It has the entity ID, because we have done a query, we somehow know an entity ID we want to kind of somehow resolve in the bitemporal plane. We have a valid time, which is ordered descending. The reason we ordered it descending is because then you can search for like anything at this point or before, basically like the reverse, like it becomes quite natural way. This is very common use in many different APIs using multi-version concurrency control. So it's not something we made up, like this kind of a pattern. Transaction time is ordered the same way behind that, and then the transaction ID is just there for good measure. We just read it out, we never use it in the actual query. The value here is the content hash, right? So this is the version. So at the bottom here you see like you will get something, this is not really true, like, but you do this DB as of this valid time, and then this will basically guide the query where to look in this thing. This is what basically binds valid time here, right? And TX time, if you don't provide it, it will be now, like as they call in the literature, as best of known, right? Like, so it's the best known valid. So we don't go back and do any auditing, we don't care, we just go into this index. So this is good. This is how Crux basically works. So this is like internally, you join these 2 indexes together, and then you find the right version, okay? So the problem with this, which we discovered after a while, is that actually my original idea was like, TX time, like you're going to have a correction, you're going to have some changes. It's not going to be that common to do bitemporal writes. Like most of the writes will be now. But then you realize there are many use cases where you're actually going to put a lot of data in the past or in the future in various other places. Well, most of those places, actually. So in those cases, you can end up having to scan for an indefinite amount of time, because you may find one TX ID or TX time, and it's like, this doesn't actually match. So I need to look at what Crux does then is looks at the next one. Is this TX time within range? The valid time will by definition already be in range. So it keeps doing that until it actually has found a TX time. This works, but it was like order of magnitude slow, like compared to our other solution, which I'm going to show before once we insert certain use cases. So we had another index, we forced the other second index, which is Z curve index. So I'm not going to explain Z curves, but if you're interested in this, go to Wikipedia, Google it, and check it out. It's very cool. It's kind of space filling curves. It's how you map multidimensional data points into basically a single dimension. There are other curves. Z curve is not the best one actually, but it's the easiest one to construct, because you actually do what this Z function does. It takes these 2 timestamps, it's descending timestamps, and interleave the bits. And that's what will happen then will mean that they are basically equal footing, right? So instead of prioritizing valid time, they are all equally bad, you could say. Like, so you don't go to this index unless you have to, because this index is slower than the other index. But if you need to look something up in the base for both timestamps, you have to hit this index. Okay? Yeah, so now I'm going to reach actually to, so this was the kind of the core deep dive of the talk. Like if any questions about that, we can talk about that afterwards. I understand that kind of blast through that a little bit fast, but now I'm actually going to talk about why would you use Crux or Bitemporality in the first case. Here are some cases I identified. I think you could do an entire talk about just this slide and motivating them and kind of discuss them, but we don't have the time. So basically, as I said, corrections, this is a simple case, like you have someone, oh, I put the wrong data in, or she didn't buy the flat at this date, I'm putting some data back in time and correcting some value, right? That's the kind of simple case. New information, this is a kind, it's not really correction, it's just that if you imagine, like real world, right, you don't know everything, so eventually new stuff comes to light, right? You add in more stuff into the database, and you can then get better, richer queries back in time. So that's one way to do it. This depends exactly on like what your use case is. Like, and both of these things require, like that's where Bitemporality is required. If you would just do this in a single timeline, you would lose auditing, right? And often auditing is a requirement in the places we use these things. So Crux comes out of a few projects in financial institutions in the UK, right? Like, or rather, it's inspired, there's no code shared, but it's inspired by some projects in financial institutions. And we realized, okay, we're resolving a similar problem. We want to kind of have a toolkit to be able to solve this problem instead of like, it's not so good to come up in the stand-up and say like, I'm going to build a bitemporal database. Like it's frowned upon. So integration is another use case. And this is one of my favorite use cases. It's kind of like the data lake use case. You just have a lot in this enterprise. Right? There are many, many systems with lots of different timelines and data, and you just want to put them in one place and start querying across. This is also why it's not schema, because you don't want to have like, okay, let's have like a 3-6 month like session just trying to define the common schema. I'm not against schema, that's not the point. The point is that we want to be able to start querying quickly. So that's one use case. So obviously, if these different systems don't agree on the timeline, having Bitemporality allows them to finally agree. So backfill, as I mentioned, I hinted at earlier, right? This is kind of one of the reasons we need this set curve in this. If you suddenly find, like, okay, I have this tape of lots of interesting data, I'm going to take it from storage and back it up, like put it up into my bitemporal database because I need all this data to do some interesting queries back in time, right? Then suddenly you start introducing a lot of data back in time. Or maybe, say, for example, you do migration from one system to another system. You may start with the live data, just put some data in this guy, right? But eventually you start kind of putting more and more data and can migrate fully to it. So that's one use. Reordering, so you have like distribution, you have systems in different regions. Basically, they don't necessarily agree on when the events, which order they came, but eventually you will get a view of a common order, right? Because you insert them, like they will agree eventually. So basically what I say is this kind of like, at least I read my abstract and I was like, oh, that's interesting, like that's not the talk I actually wrote. So, but it's like immutably in the large, right? Like, so this like, once you start thinking in this way, it's almost hard to go back, right? Because you are kind of constrained by kind of like a functional programming, you know, romantic fairyland, right? Where everything, you never need to change anything, right? And everything is pure. Or you get like this kind of like horrific update in place thing. But Bitemporality kind of tries to give you a little bit of both, best of both worlds. As you get a lot, you can basically change your mind. But you don't necessarily need to, you still know that you've changed your mind, if that makes sense. Yeah, so when we first started building Crux, we sat down, or rather Malcolm and John, who are the owners of JUXT, right, or the founders of JUXT, they came up with Crux, if I understand correctly, somewhere in Sweden, apparently. And they had a few constraints, a few requirements, and we sat down and kind of ironed them out. So I was going to go through from originally what Crux today is a bit different. We are going to different places, but it's kind of where Crux started, right? So again, now we're kind of repeating it a little bit. We wanted bitemporal time slice queries because that's the kind of actual use case we needed to solve in some cases. We needed Datalog. We didn't need it, but we wanted Datalog in the bottom because it's very powerful and nice to work with. We wanted lazy results, right? So some, like, it's very useful to be able to stream the result out. You have a massive result set, right? To not be constrained by memory, to have to put the entire result in memory. So we looked into that. And we wanted, because of course, value and transaction time is the kind of, yeah, that's the definition of bitemporal time slice queries. We wanted easy ingest, right? We wanted the ease to get started with. Like, okay, we want to get something happening right now. Just get some data in. We didn't want any schema. We didn't want any back pressure. Back pressure is awesome, right, and has its places. But in this case, we just wanted to blast things into Kafka. And then, because some of the integrated systems we want to talk to, they may be hard to talk to. They may be slow. You may only be allowed to talk to them in certain times. So we basically have to kind of just let's get the data out, and then we put it into Crux, and we'll see what happens, or the precursor to Crux. We wanted cheap eviction because we needed GDPR, right? So we needed something that allows, so it's kind of implicit in the slides I showed before, but it's not very clear. It's like, when we put this one design, which was quite hard, it's like trying to figure out, we don't want the different, if you look at how it worked in the SQL case, they updated rows, right? Like when you insert a new thing, you also need to update some of the data in the other rows, but we didn't want the rows to be dependent on each other, because that means it's going to be much, much harder when you want to get rid of rows. So one of the things, we didn't want to have a lot of impact when you kind of took away something or added something. So we don't rebuild the entire index when we basically remove something from it. Yeah, and we also wanted a small unbundled core. Right, so we wanted to build it and then build it in layers. And this has been relatively working quite well. Now a lot of the work in Crux does not happen in the core. It happens in modules outside core. It also stops a lot of arguments, like someone wants this thing, someone wants this thing, okay, like build a module. And then you can have some requirements on the core, and the core needs to basically provide capabilities for that. We also, we kind of admit, like it needs to be realistic engineering. We didn't want to go from like a multi-year research project. So Crux has basically been going 1.5 years or something. Like, and we started working on it, or I started working on it in earnest last summer. And at that point, John was already at it. He had already written the first version of Crux. So the first thing I came in and did, he had written a Datalog engine on RocksDB, and I came in and added the Kafka part. And then basically I rewrote this Datalog engine and added some other parts. So basically, we're a small closure team. We bootstrap our JUXT. It's very hard at, I always say that mistake now. So we cannot like, we want, as I said before, we have single nodes, they're all the same, they're all the functional log, there are lots of other funky, cool, distributed things you could do, but it's something we want to build something new that actually could pull off, right? That doesn't mean that Crux 2 or Crux 3 are going to be much, much more advanced, right? But let's start somewhere. Again, some people say, don't put this on the slide, but we actually didn't have written a database, none of us, properly, right? Who really does that, right? Like, so, but we have written a lot of these kind of applications, and if you think about it, a lot of application developers these days are forced to become distributed system engineers without really wanting to be, right? Because they have all these microservices and event streams and all kinds of things, right? So we kind of exposed enough to the space to understand some of the problems we need to kind of patch up and avoid, right? But we got some experience now, and it's been like, yeah, we've been reading so many papers and thinking and debating. It's been, to be honest, this has been one of the most interesting and exciting projects I've been working on in my entire career, right? Which, I'm not sure if that says much, but it says something. Okay, so it must rely on proven tech, right? We did not want to redo like the B tree and the kind of disk-based indexing, right? Like, so we kind of, sure, maybe later down the line, there's a time and place to rewrite, not rocks, you don't want to write rocks, but write something that is exactly the use case you need for your KV store. Same thing for your distributed log. Maybe change all this together, but at the moment, we kind of just, yeah, let's start somewhere. Okay. And we also, one other requirement, like a realistic, like we realized we cannot do everything ourselves. We want to build a small core, we want to get people involved into the core. We're not entirely sure how that process is going to work, but we want to have people, as I said, several people in the open source community have already written modules for Crux, which are building on top of the core. So we start there, potentially we may have some process to get people actually involved in the core. I think the problem with the core at the moment is not so much we don't want pull requests. It's a little bit opaque, right? I must admit, it's not like super obvious, like how to actually change something in the, we have a few very dense namespaces in the middle of Crux. So yeah, so that's kind of, I guess our goal is kind of to go to beta and stabilize the API this year. And then we have some exciting ideas for next year, assuming everything works out. But I'm not sure, I don't think I have time for questions, but otherwise just find me afterwards, or if I have time for questions, I can potentially take some. But thank you very much, Crux.
Hello, great
Hi.
talk.
Thank you.
I was just wondering, I have a question about the eviction strategy.
Yeah.
Basically, what I understood from your talk was that you leave holes in your index.
Yeah. So
how, on the query side, do you distinguish between an evicted hole and, for example, network outages? So, like a missing document when you're getting a sequence of things, for example, related to bank industry?
Yeah, so one thing I didn't mention was that we never transact before we have all the documents related to that transaction, right? So there's it's not as simple as we just read these topics and then basically start indexing. Like for a while it was like that, but then I realized that actually doesn't work, does it? So basically all the transaction topic gets paused and resumed in Kafka all the time until all the documents that exist. And because we put tombstones into when basically we have evicted something, we know that the document kind of still exists in a sense. So we wait for either the real document or the tombstone to appear. Like we don't use tombstone for deletes, right? We only use them for eviction. And in practice that means that yes, your queries will, it basically treats in the query and it treats it as a delete, basically. So suddenly a query, so this is like, I should have mentioned this, but you get repeatable reads in Crux by providing both valid and transaction time, right, to your DB call. But eviction is the thing that breaks that because there's no way around that. Like if someone really wants to get rid of the data, of course we have to get rid of it, and then suddenly your query may start returning something else. Okay, thanks.
Was Datomic an influence for something you wanted to be like or different from?
Of course it was an influence, but it's also something we want to be different from because we're trying to do certain things which Datomic doesn't do. I mean, I've taken some design decisions. Also, one thing, as I mentioned, the last pointer, we wanted to be open source. So one thing that I also wanted bitemporality. So these are the kind of main differences. And I've been very adamant that we don't, there's another thing called EVA, which is more like a Datomic clone, an open source clone of Datomic, which you can find on GitHub, which I don't remember what the company's called that's built it. We didn't want to do that. Like I've been trying to kind of move the API away. For a while I was even trying to get like proper, Prolog style Datalog into the query engine, but that kind of was overruled at some point. So we try to solve slightly different use cases. We don't have schema, and well, I'm happy to talk more about the other afterwards if you want to.